nonlinear optical responses of topological chiral semimetals. Professor Wu got his bachelor degree from Nanjing University in 2010 and his PhD degree at Johns Hopkins University in 2015. After that, he worked as a postdoc at University of California, Berkeley. Now he is in University of Pennsylvania. His research focuses on Terahertz spectroscopy and nonlinear optics to study non-topological materials and quantum magnets. Due to his outstanding contribution, Professor Wu has got the APS Richard L. Green Dissertation Award, William L. Macmillan Award, and the OCP Macaronic Prize. Hi, Professor Wu. Now the stage is yours. You can start your seminar. Thank you.
Okay. So good morning, everyone. First, I want to thank Guoqing for the invitation. Therefore, I would like to take this opportunity to tell you about the nonlinear Terahertz Emission Spectroscopy on topological chiral semimetals, which was actually predicted by Guoqing like 4 years ago. Okay, sorry. Good. Yeah. So first, I would like to thank my student and my collaborators on this project. So the nonlinear optical measurement was done by my student Liang, and the linear optical conductivity was done by a postdoc Bing Xu in the University of Freiburg. And the calculation for the DFT density functional theory calculation was done by a postdoc Yang Zhang at MIT. So he worked with Liang Fu. And the time binding calculation and the K.P model were mainly done Fernando de Huang and Adolfo Grushing and the students Oscar and Michael. And we have lots of ongoing collaboration at PIM on these projects, which I think I might not have enough time to talk about today. And also the nice crystals are mainly from Claudia Felser's group and Jean-Pierre Paglian group at Maryland. Okay, so this is the outline of my talk. In the beginning, I would like to introduce what do I mean by topological nonlinear optics. Then I want to introduce what are chiral multifold fermions and also how do we see them in optical activity in the linear response in the example of cobalt silicon. Yeah, so my talk will be mainly focused on cobalt silicon. So then in order to see the contribution of these multifold fermions in the photocurrent, so we developed Terahertz emission in the mid-infrared regime, in this energy regime. So then I would like to show you that how do we use Terahertz emission spectroscopy to measure a giant topological longitudinal circular photogalvanic effect in cobalt silicon. Then in the end, I think I will show you one slide on Rhodium silicon, which was originally predicted by Guoqing a few years ago. If I have time, I might show you some data on the chiral antiferromagnets, which are not topological at all, but it's quite interesting in a different aspect. Okay. Oh, by the way, feel free to stop me if you have any questions. I think we have enough time. Okay, so first let me introduce what do I mean by topological nonlinear optics. Okay, so first I will say that so we have known the topology actually for a while. So here, when I say topology, I really mean that a response that is quantized in the unit of some of an integer times some fundamental constant. Okay, so I don't mean like vortices in superconductor, for example. So the first example that of the topological invariant that show up in the linear response was a quantum Hall effect that was discovered by von Klessen in the 80s. So then another maybe famous example in the magnet-doped topological insulator was a quantum anomalous Hall effect in the 2013, and also in the linear response, we know how to measure the topological invariant, for example, by the Faraday and the Curry effect in topological insulators on the magnetic field. The rotation passing through the rotation of the light passing through the sample will be quantized. So this was done when I was a student with Peter Armitage at Hopkins. Okay, So basically, we know the concept of the topology very well. I mean, from the quantum Hall effect, then like topological insulators and Weyl semimetals, and we know how to measure the quantized response in the linear response regime. And we also know nonlinear optics very well. Since 1960, which was predicted by Bloomberg at Harvard and discovered very soon after that. So like in experiment, I mean, people measure like photogalvanic effect or photovoltaic effect. And here I don't talk about p-n junctions. I really talk about like some materials that break inversion, like ferroelectrics. Okay, and we also know how to measure second Harmonic generation to figure out the crystalline symmetry or other some magnetic properties. But before I would say before 2016, so the link between topology and the nonlinear optics were not clear. In other words, whether there was a response that is quantized in the topological invariant was not clear before 2016. So this is what do I mean by topological nonlinear optics. So I'm interested to measuring some nonlinear optical response that is quantized in the unit of like finite track constant and the topological invariant, which we call a number. I will introduce in the next slide. And maybe a practical kind of application or the practical another motivation for this kind of study in terms of practical application is that we were wondering whether we can find like photovoltaic better photovoltaic material based on topological materials instead of p-n junctions. In other words, whether we can find a material that can convert light into current more efficiently, because here we are really dealing with hot carriers. Okay, so it's a different mechanism from p-n junctions. Oops. Okay, so first let me introduce what are Weyl semimetals and what are the Chen numbers. So here is maybe the simplest kind of a model for the Weyl semimetal when you break tangle symmetry. Let's say you have two quadratic bands, okay, and you will have linear crossing. I mean, the linear crossing is really three-dimensional, but we can only draw it in two-dimensional. So here, basically, this is linear crossing in three-dimension, and we call these Weyl points. Okay, so this is kind of like a 3D version of graphing, because we know that graphing, it has linear dispersion along like KX, KY direction, but there's a fundamental difference between like the graphing and the Weyl semimetal is that because in Weyl semimetals, we already use the kind of three poly matrix. So actually when you have some perturbation, for example, the sigma z perturbation, you just move the Weyl point in the momentum space. So these points are very stable. They are generally gapless. It's not like graphing. So graphing, if you introduce like a sigma z perturbation, you can really gap out the graph point. Okay, so that's why they are topological, because they are really robust if you add some perturbation. So you're basically moving in the momentum space, but don't gap them out. And in order to have the Weyl semimetals, so we need to break inversion or the tangle symmetry. And today I will basically talking about the breaking the inversion broken case. Okay, so another way to view why the Weyl semimetal are topological is that so here is the Weyl point, and here there is something called a barrier curvature. So this is like the momentum, like the magnetic field in the momentum space. And if you use the calculate the flux of the magnetic field in the momentum space and divide by 2 pi, so this is integer. So this is a Chen number. And you can also understand the Chen number as charge of the Weyl points in the momentum space. Okay. So secondly, I would like to introduce what nonlinear optics. So and I really want to focus on second order response. So let's say that we have a pulse centered at frequency omega 0, and of course it has some distribution. Okay. And if we shine a nonlinear crystal that breaks inversion symmetry, I mean, the common response that people see is the second Harmonic generation, which is the omega plus omega response. But for example, this is the crystal, the BBO crystal that is widely used in like light conversion. If you shine like red light on the crystal, and if you find the right angle to do the phase matching, then where you will see a bright blue light coming out of the crystal. But today I would like to focus on the circular photo on the other response, which is a photogalvanic response, which is omega minus omega response. So if you are shining a continuous wave laser in a single color laser, so what you will get is really exactly omega equal to 0 response, okay, omega minus omega. Nevertheless, if you're shining a pulse on the sample, because you have frequency distribution, so what you get is really omega 1 minus omega 2 response. And it turned out that this different frequency is in the terahertz regime. So that's why if we shine a pulse on a sample, we will get terahertz emission from the transient photocurrent, which is the focus of my talk. A few years ago, when I was a postdoc with Joe Ornstein at Berkeley, we were very fortunate to discover that in the Weyl semimetal tantalum arsenic, that the second month generation is really like 2 orders of magnitude larger than gallium arsenide. Okay, so here the gallium arsenide is times by a factor of 100, and gallium arsenide was known as a material with the largest Chi2 in the infrared regime. So this signal was really large, and later on there were photogalvanic effect work. So in the community, they measure photocurrent and also saw gigantic photocurrent from the same crystal. Then a natural question that the community asked and also we asked was that whether this large optical nonlinear entity is related with the Weyl nodes. Okay, it turned out that the answer is not easy to give actually, because 2 reasons. First is that so we call this energy Lifshitz energy. So basically below that, the excitation are mainly near the Weyl nodes, and if you're above that, then you can have like excitation from Weyl node to maybe chiral bands, or from chiral band to chiral bands. And this energy is very small in tantalum arsenic, and it's like 85 millieV. So I have to admit that you can see that my earlier work, the photon energy is too high. So we don't exclusively excite near the Weyl point, and also in the photocurrent measurement, the photon energy is also a bit higher than the Lifshitz energy. A second complex issue is that near the chemical potential is not just like Weyl bands. There are like trivial electron and hole bands. So we also have excitations from other like quadratic bands. Then the origin become less clear. So this is one of the reasons that we move on and we're trying to find clean materials with only topological bands at the firm surface.
Hey, Liang, I had a question about your previous slide. So you're saying that this very large second generation in tantalum arsenide, because of the very large energies that you're at, 0.8 eV, 1 eV, it's very far away from the Weyl nodes and may not have a topological origin. Is that what you're saying, or no?
Right. So experimentally, I would say it might not have topological origin.
I see. But is it understood? Is it understood what is causing the 200 times larger?
Right. Yes.
Than gamma arsenide? It doesn't have to be a topological reason, but just any reason.
Right. So yes. So as I said, experimentally, I would say we don't have a direct evidence. It's enhanced by the Weyl points, but theoretically, there was a paper by Nagosa and Binghai Yan. So they had their explanation is that so even though the photon energy is high, so basically here we have 2 Weyl bands, okay, but there's another highly high-lying band, maybe somewhere here. So now the nonlinear optical process is related with 3 bands. Their argument is that if 2 of the 3 bands are the Weyl bands, then this contribution is much larger than 3 chiral bands. So
it's not just a resonant absorption kind of thing that is enhancing it. It's something else.
Right. So it's really kind of a 3-band process. It's also related with the virtual.
And that's that ERB. Yeah. Okay.
Yeah, but this is a theory, and for experiment, I mean we can. I mean of course we can measure spectron and compare with the theory, but we just haven't done that yet.
Yeah. Okay. Thanks. Yeah. Thanks a lot. Yeah.
Okay. Yeah. Right. Okay. So the second reason actually maybe more fundamental that why second half generation or the I forgot to say that here actually the large photocurrent is that when you shine linearly polarized light, that's called a linear photogalvanic effect. So a fundamental reason why like second half generation and the linear photogalvanic effect are not related with like Chen number are the following. Okay. So it was really developed in the 80s by like German and Russian, and also like SIPE and Nagosa use different methods, but their formula in the end is really the same. So the message is that for second order generation and the linear photogalvanic effect, so in the end that the second order connectivity is related with some quantity, some gauge invariant quantity called shift vector with some selection rules here. So the meaning of the shift vector is that really you shine a light, then the electron cloud shift in a real space. So that's like current. So yeah, so here is the message. So they are related with a quantum geometric quantity, which is a kind of gauge invariant shift vector instead of the Barry curvature. So that's why we study like circular photocurrent in the materials in cobalt silicon. Okay, so as I said, before 2016 or maybe 2017, there was no prediction that a nonlinear second order response is related with the Chen number. So first it was done by Fernando de Huang in the Joe Morse group at Berkeley, and later, I mean, soon after, also Guoqing and Hassan, Zahir Hassan, Princeton predict in like rhodium silicon that I will talk about in a moment. So their idea is that, so here, let me say one more thing. So in tantalum and arsenic, because you have mirror symmetries, so the Chen number with opposite charge are at the same energy. So here, the idea is that if you break mirror symmetry, so the Chen number with the opposite kind of number, for example, +1 and -1, they happen in a different energy. And if your chemical potential is between them, and if your photon energy is low enough, so you can polyblock this excitation on the right cone, so you only excite near the left cone. So you have the chance to measure the Chen number from the left cone. That's the idea. Unfortunately, I mean, they predict like Chiral Semimetals, but none of them exist in nature for some reason that we don't understand. So I think this is why like Guoqing's work was very important, because he predicted that rhodium silicon have this kind of effect. So this is a kind of the band structure of the rhodium silicon, which I will introduce in the next slide. And the real band structure here is just maybe cartoon. So instead of like two bands, it has like multi-bands. That's why it's called multifold semimetals. For example, at the zone center, the gamma point, it has like two linear bands and one flat band, and the Chen number is not like 1. It's like -2, 0, and +2. And at the zone kind of boundary, so then we have so basically this is like two copies of Weyl points on top of each other. We call this double Weyl fermions. Okay, so the Chen number is also doubled from here. The idea is the same. The points, the topological points are at different energy, and if the chemical potential at the right place, if the photon energy is low, you polyblock one of them, then it's quantized because of the left one. Okay, so what's quantized is something we call circular photogalvanic effect. So basically, you shine light, you shine circular polarized light, and you have a current J, and you switch the helicity, then you have another J. So then you need to take the difference between the left and the right, and also take the time derivative. Okay, so what's quantized is not current, but it's dJ over dt. So it's the rate, the change rate of the current, and this is the electric field, and this is a coefficient. And also, what's quantized is really the trace. So this is the kind of diagonal part. You need to sum over like beta xx, beta yy, beta zz. So that's quantized in the linear model. As you can see, it's the integral of the interband Barry curvature, and in the end, it's fundamentally constant in the Barry curvature. And this was a time banding calculation of rhodium silicon, and they predict that below 0.7 eV, it's quantized. It's like very close to 4. Okay, yeah, but I mean, we also study rhodium silicon, but my talk will be focused on cobalt silicon, because this material is actually cleaner than rhodium silicon due to the crystal growth method. So why do we call them chiral? So basically, if you look at they are in the cubic structure, and it's the famous B20 crystal structure. So if you look at 111 axis direction, from top to bottom, for example, like in one of the, for example, if it's the left-handed crystal, so the cobalt atom wind in a right clockwise way, and the silicon wind in an opposite way. And if they are in a, for example, right-handed crystal, the cobalt will wind in the opposite direction. So that's why they're really chiral. It's like helix or like DMA. Okay. So this is the real band structure measured by angular photo emission. So you can see that at the gamma point, it's really like a flat band and two linear bands. And at R point, it's Weyl, double Weyl. And in the cobalt silicon, the spiral coupling is very small. So they cannot really see the splitting here. So it's like a doubly degenerate bands. But optics can, because our resolution is higher than like 20 million eV. So first, we want to confirm the existence of the multifold fermion, on top of the angular photo emission experiment. So what we did is optical connectivity. So here, I just want to show you the band structure again. So this is the band structure by DFT. So this is the band structure without spiral coupling. So you can see the threefold fermion here, and this is double Weyl. If you consider, so this is a threefold fermion again, and if you consider the spiral coupling, so this threefold is really sixfold, because there's a spin degeneracy of 2 here. So the sixfold will split into a fourfold spin 3/2 fermion and a twofold double Weyl. Sorry, the twofold Weyl fermion here. And this is really a eightfold fermion. It will split spin 1, a sixfold spin 1, and a Kramer pair here. And you can see that in the other chemical angel, we only have the threefold excitations and also double Weyl. There's no really trivial bands. So that's why we really like cobalt silicon. It's really ideal. So as I said, the first thing we measure is the linear conductivity. So this is the linear response. So that's a J equal to sigma E. Okay. So we measure the conductivity as a function of frequency, and the blue is the raw data. You can see that there's a Joule response and a very sharp phonons, then the conductivity increase as a function of energy. So then what we did next is that we fit the Joule response and the phonon peak, and then we subtract the raw data by the Joule response and the phonon. So what's left is this red curve. So this is the interband from band to band transition. So you can see that we have a 2 quasar linear regime. One is from 0 to 0.2. So here 0.2 eV, then another quasar linear regime. It turned out that, so you can see that this R point is 0.2 EV below the chemical potential. So the first quasar linear slope is really about excitation near the gamma point. So about threefold fermions. Then above 0.2, the R point is turned on. The excitation here is allowed. So that's why you have a different slope. What's nice in this material is that so this is the whole band. Okay, so this is a very heavy whole band, and here you have an electron band, and the electron band, because of velocity, fermion velocity is very high. In other words, the mobility is very high. So when you do transport in whole conductivity, you only see the electron part. And in other words, then the Joule response, which measure the free carrier behavior, we are also sensitive to the electron pocket. Then we can measure something we call spectral weight. So spectral weight is the area below the real part of the conductivity of the Joule response that is proportional to the carrier density divided by the effective mass. And from the temperature dependence, which is T squared, we can get the coefficient, which we can figure out the fermion velocity. It turned out the experimental value from the measurement agree with the DFT very well. It's like within like 9%. Okay. So yeah, that's a Joule response. Now let's focus on the quasar linear response, which is the band-to-band interband excitations. So we also perform the DFT calculation. You can see that in experiment there is a prominent peak at 0.56 eV, and also in the DFT. So what's the origin of that? And you can see that if you calculate the joint density of states, there's a plateau at 0.6. And if we do some momentum Rudolph contribution of this peak in the momentum space, you can see it's really from endpoint. So actually the endpoint is the saddle point. Nevertheless, the the message here is that so above 0.6 eV, the endpoint is turned on. So these are really trivial excitations, excitation from trivial bands. But below that, so below 0.2, it's from the gamma point only, and above from 0.2 to point, let's say 0.56, it's mainly from R point. In other words, below 0.6, they are mainly from the multifold bands, which are topological excitations. The second thing is that so this red curve is the same red curve here, okay? So it's from the interband excitations. It turns out that if you use the calculation when we consider spin coupling, it describes the data better compared to without spin coupling. So this is basically evidence of the splitting, the band splitting here, which is like 20 millieV. So yeah, so we have evidence for spin 3/2 quantum particles. Yeah, so here I just want to emphasize again. So basically, we need to go below 0.56 eV to have excitation near the multifold fermion. So that's why we developed Terahertz emission in the meta-infrared regime, actually, for the first time. So before that, let me tell you about circular photogalvanic effect. And I want to focus on the longitudinal circular photogalvanic effect, which was pretty rare, actually. It was first observed in chiral toluene in 1979. Then actually the second example, maybe third and fourth, were really in the past 3 years on cobalt silicon, rhodium silicon, and on titanium disolenide. So longitudinal CPGE really means that if we shine like circular polarized light, let's say right circular polarized here, the current flows down. So the current direction is along the wave vector direction inside of material. And what's more common is something we call transverse CPGE. So transverse CPGE means that the current is perpendicular to the wave vector direction. So this is more common, like in tantalum arsenic or like in like transition metal dichalcogenide. It's very, very common. And what's cool about longitudinal CPGE is that if we switch the helicity, if we make it left circular polarized, the current actually is going up. So you're kind of pumping charge out of the system. So then here, if you're shining a CW laser, in other words, single color, you will get a DC current. And if you're shining a pulse, as I explained in the beginning, so what we will get is a transient current. And in the far field, so the first derivative of the transient current is the Terahertz emission, okay? And also, like for the quantized CPGE, and what's quantized is really the DJ over DT, is the first derivative of the current. So that's why we measure Terahertz emission for the photocurrent instead of a conventional like DC current one. So this is a conventional kind of method, or mostly mostly used method. Basically, people put contact on the sample, then shine like a laser spot here to measure the current. Nevertheless, there are a few things that one needs to be very careful with. One is that you need to align the contact along the crystal axis. Second thing is that if the laser spot is not in the center, so you have heat gradient, thermal gradient, you can have a thermal current. And then there's another complex issue that if the laser spot is smaller than the sample, you need to deal with like carrier drift or carrier diffusion. Actually, I think Justin had a paper on graphene on this topic. I mean, my group is not used to do like DC photocurrent measurement, so we decided not to follow this method. Because we don't want to deal with these issues. I mean, if you're careful, you can deal with them, but we decided to skip the 3-step to measure the photocurrent. So that's the way we use the Terahertz emission. So we're not the first group to do Terahertz emission. Actually, at the NTU, I mean, Professor Chair also did lots of work on like, for example, like spin-hole emitters. So, I mean, lots of work in the community. But as I said, so we are the first group to push in the meta-infrared regime. So the idea is we shine a pulse laser and then we have a transient current. And we do off-normal incidence so that there's a surface component that can radiate Terahertz in the far field. Okay, so DJ over DT is the Terahertz field. And Terahertz is very important for condensed matter physics because energy scale is like 4 millieV or like 50 Kelvin. For example, like the magnons in antiferromagnets are in the Terahertz regime, and the binding energy of the cool pairs are also in the Terahertz regime. So my group are doing lots of research on the topic, but today I won't I won't tell you about that. Another nice thing about the Terahertz emission is that there's no contact. So then we can really align the crystal axis by second generation very well. Even though in this case, actually due to the cubic symmetry, we don't need due to the cubic symmetry, actually the crystal rotation doesn't matter. But in other cases, you can align it very well. So you can see that how much that it really take to go to the mid-infrared regime. It really cover like 1.5 2 tables in order to Terahertz emission in the mid-infrared regime, and also that to couple with a cloud stack. Okay. So now let me focus on the major part of my talk, which is a giant topological circular photogalvanic effect in cobalt silicon. So in order to show that it's longitudinal, so we basically introduce like polarization dependence. We control the polarization dependence of the incident pump and also measure the terahertz in the incident plane and perpendicular to the incident plane. So here I just want to show you the result that we measure the terahertz kind of polarized in this yellow plane we call incident plane. Okay, so you can see that indeed if we switch the helicity of the light from right circular polarized light to left circular polarized light, the polarity of the terahertz flip, which really means the transient current flip. But nevertheless, how do we know this is longitudinal CPGE? So we need to do more like polarization dependence. So the first thing let's look at is let's look at the terahertz emitted in the z-axis, which is perpendicular to the incident plane. Okay, so here let's look at the yellow curve or the gold curve. So you can see that between left and the right circular polarized light, the terahertz signal has the same like magnitude and same sign. And if you look at the raw data, they're really on top of each other. And as I introduced in the beginning, the CPGE is really the current between left circular polarized light and the right circular polarized. So you need to take the difference. So if you use left minus right, the difference is a gold curve here. It's like almost 0. And also if you take a sum and divide by 2, actually that's a linearly photogalvanic effect. It's very large. So basically no CPGE in the direction that is perpendicular to the incident plane. Now let's look at the circular polarized, now let's look at the terahertz emission in the incident plane that I showed you 2 slides ago, but in a more detailed kind of polarization dependence. That's a blue. So first thing you can see that from left and right, the change sign, right? Also in the raw data, they really flip. Nevertheless, if you look at again, this is different in CPGE, but they are not like just a mirror image of each other, because if you take a sum, it tells you that it still have the LPG, but the CPGE is much larger. So here we're basically showing you that the CPGE is only this in the incident plane. Actually, there's a simple explanation for that, which is the longitudinal CPGE. So when the light is incident in the incident plane, so that the wave vector or the current in the material is also in the plane. Okay, and so it will have oscillate in the incident plane, and the surface component is oscillating also in this plane. So that's why the emitted terahertz from the CPGE is in this plane. This is really consistent with the longitudinal CPGE in cobalt silicon. So we confirm it's longitudinal CPGE. The next thing we want to figure out is the magnitude. In other words, we want to measure the dj over dt or the j. So as you know that in the linear response, we can have the j equal to sigma e, right? That sigma, we have a Joule model. There is also tau. And here, so this is kind of like the second order conductivity of the photocurrent. So j is equal to, I call this quantity eta. Okay, so this quantity is eta. I call this eta e squared. And here the tau is not like the backscattering time in the transport. So this tau is the hot carrier relaxation time. So that's the difference. And there are 2 regimes. One is that this hot carrier lifetime is very large. Sorry, I forgot to say that this big omega is a terahertz frequency. So when you have a pulse, so different frequency inside the pulse at the terahertz frequency, we use big omega. So this is different from the incident photon and the little omega here. So there are 2 regimes. One is that the lifetime The hot electron lifetime is very large than the 1/Terahertz frequency. So this is actually in the quantized regime that like Joe Moore or Guoqing predicted. So basically dj/dt is quantized. Okay, so this beta xx is like a 1/3 of this value. So as I said, so this material has cubic symmetry. So and what's quantized is really the trace. So it's beta xx, beta yy, beta zz. Because of cubic symmetry, they're the same. So we only need to measure beta xx, and if we multiply by 3, so that's a trace. It's a beta 0. The second regime is the hot electron lifetime is much less than the 1/Terahertz frequency. So in this regime, actually, we the J is related with the beta, is with beta times hot carrier, and unfortunately, actually, we are in this regime. The tau in this material are too short, so we are not in the quantized regime yet. We are in the saturation regime. So then, as you can really see from the eta. So the eta, you can see the expression for the eta is like this. So if omega and 1/tau is on the same order, we will basically see something like a curve, some frequency dependence, really like the Jude behavior in the linear response regime. But here it's really flat, which means that the tau is really small. So we can really forget about the omega term, because when the tau is very small, this term is very large. You can neglect this, then basically it's beta x times tau. So then what we plot in this plot is that, let's say that we have incident photon energy at 0.25 eV. So in the Terahertz regime, so this is a big omega here, it's really flat. So we take the average, frequency average, then we plot the eta here. So this is the eta here, which is beta x times tau. So this is 0.25 eV, and then we can change incident photon energy, still measure the Terahertz emission. So then we have a spectrum. Sorry, I forgot to say that. So here we were doing in the time domain, then we do Fourier transform, go to the frequency domain, and we use some like benchmark material, like of zinc telluride, to figure out what's the eta. Okay, sorry about that. Yeah, nevertheless, so this is spectrum. So this is incident photon energy. This is the beta x times tau. So two things here. One is that this actually is very large. It's really like 600 microamp per volt squared. So if you look at the bulk photovoltaic effect in like ferroelectric material, this is really like 1 orders magnitude larger than that. Secondly, so if we look at the peak here, so what we can do is that I will show you on the next slide. As you can see that from the density function theory, the curve actually match the data pretty well. So what the density function theory can calculate is really the beta xx. So there's no free parameter. If you have band structure, then you can really calculate the beta xx. And so what we do next is that we use tau as a fitting parameter. So the peak is depend on beta x times tau, and the width is actually also depend on tau. So we can tune the tau to let it match the peak and the width. Actually, so only one fitting parameter. So we can figure out both tau and beta xx. You can see that it matched very well. And also spin coupling doesn't really matter that much, because spin coupling is 20 millieV, and we are really measuring at much higher energy. Another thing we can do in the density function theory is that just figure out the momentum contribution at momentum result contribution at this 0.4 eV. You can see that it's really an R point, which is the double Weyl, and the gamma point, which is 3-fold. So there's no contribution from M point. So in other words, this peak is really from multifold kind of bands, and actually it's only from the multifold bands, and it's mainly coming from R point. Okay, so that's the two message here. So even though it's not quantized, but it's very close to 4, which is the number of the kind of the double Weyl. So it's like 3.3. So you might wonder why it's not quantized and how we make it quantized. So this actually bothered us for a long time. That our data was really different from theory predicted. So then, yeah. So then, actually, in the early theory, so what they did is that they put the camera potential actually above the flat bands. So then basically, if you put about the flat band, so the excitation from band 1, band 2 are polyblock, and only from band 2 to band 3, so that gives you quantized. So that's a curve here. Okay, so that's the curve, the green curve here. So the chemical potential is like 33 millieV, so that's like above the flat band. So this agrees the early calculation, for example, on rhodium silicon. Nevertheless, I mean, the crystal is a compensated semimetal. So it has hole pocket here, and it has electron pocket. In other words, the chemical potential is below the flat bands. So this gives you some like kind of complicated like transition as function of energy. So you can see that it actually, if the chemical potential is below the flat band at low energy regime, it can quantize, but the window is very narrow, and you have a zero crossing, then you have a peak. So actually what we measure is really this non-quantized peak. Okay, so this red curve is at room temperature, so it's the same red curve here. So you can see that we have a peak here, and at room temperature, this dip is not quantized. We really have to go to low temperature and have much longer hot carrier to see this is quantized plateau. And it's better to that dope the materials above the flat band so that the quantized plateau can be much wider. That's the conclusion why it's not quantized. So this is a DFT, to explain the data. Then Fernando de Juan developed a very simple model, which is the KW model. So KW model is really linear bands, but as you can see that these bands is not like perfect flat, it's bent down. Okay, so what does bend down mean? That we need quadratic correction. So this is the K dot P. Then we have a kind of the quadratic correction. So then his student Oscar and Fernando basically fit the DFT band and figure out these coefficients. You can see the KW model is this orange curve, blue and the green curve. So then they can really predict the zero crossing actually, because the chemical potential is cutting the flat band. So and also there's a very interesting kind of behavior of the excitations. So when the chemical potential is here, so the first excitation happens from band 1 to band 2. When that happens, we're in the quantized regime. Okay, we're in the quantized regime. Then of course, I mean, when the energy becomes higher, the excitation here will become less and less. So the quantized is lost from band 1 and band 2. And when the energy is high enough, so then from band 2 to band 3 is allowed. But this is from band 2 to band 3. But that's not really quantized because we still have the contribution from one and so because that's not quantized because there's some quadratic corrections. Okay, so you can see that it's not really quantized, maybe at high energy. So then at the gamma point, the total contribution is from band 1 to band 2 plus band 2 to band 3. So the total contribution is the blue. So quantize here, then quickly lose quantization. So then for the R point in the model, we just use very simple step function. So basically here it's polyblock. Then when R point is allowed at point 2, it has a step function to 4. Okay, so this is the R point, and this is the gamma point from the KW model, and the total sum is this green dash curve. If it's not clear, so it's like really plateau, then lost plateau, then zero crossing, and the peak. So what we measure is really this peak, and mainly from R point, and we exactly saw this. Sorry, we didn't see the zero crossing yet because in cobalt silicon, the zero crossing is below it's really below 0.2, and we cannot really measure 0.2 in cobalt silicon. But we predict that there's a sign crossing if the chemical potential is below the flat band, and this can be seen in rhodium silicon, which in the next slide. So the difference between rhodium silicon and cobalt silicon is that rhodium is much heavier, so that the spinor coupling is much larger. So you can see that the energy splitting between the threefold between one of the node and the second node is much larger. And because of that, this zero crossing is pushed like above 0.2 EV. So you can see that the blue is the data. And again, this is a CPGE current. So you can see it has a zero crossing. And if you put a chemical potential below the flat band, it really match the data pretty well. Okay. Nevertheless, as I showed you in the beginning, so this is kind of drastically different from the tight bending model calculation that Flicker and Fan did earlier, and also Guoqing's PIL in 2017. That's because, as you can see here, if you put chemical potential above the flat bands, okay, so this is 100 millieV, it's really like here, so you can see it has a, sorry, here it's upside down, okay, so here it's like this shape, but here it's going down, but if you flip it, it's basically like the same kind of trend. Yeah, so that's really the reason which bothered us for a long time. So because of the cutting the chemical potential, it has a zero crossing instead of plateau. Yeah. So then this actually explained the similar work on rhodium silicon from two different groups. We have a similar conclusion and similar data. So then in order to see the quantized CPGE, I mean, there are a few things that we're working on. One is that we're doping the chemical potential above flat bands. So we're working on nickel. Sorry, maybe I didn't put here, but anyway, we were working on nickel doped rhodium silicon, and the chemical potential is really above the flat band, as you can see from this photo emission data from the Sun group, and also calculation from Guoqing. So we're trying to measure this quantized CPGE in this doped rhodium silicon, and we're also doping cobalt silicon. Maybe, I think I still have time, maybe I want to put another note. So one thing is that you can see that the plateau in rhodium silicon from DFT is less nicer than cobalt silicon, because here the spinor coupling is so large. And actually, even though, like let's say at low energy, let's say we only have a kind of excitation near the gamma point, because here we have energy splitting. So when our point, when this excitation is polyblock, but from the here the split band, so here is allowed. So this contribution is very large in the silicon. That's why here the quantization window is not great. And the cobalt silicon is much better because the spinor coupling is smaller. So we hope that our collaborator can dope the cobalt silicon so that we'll try to see quantized CPGE or not. Okay. Yeah. So maybe. So actually, do you have questions? I can skip my last two slides because it's already 15 minutes actually. So what do you prefer? I can go to my conclusion and then maybe look for questions on this part, because I mean this part is not really with topological. It's not really with CPGE, even though it's chiral.
Yeah, I think you have enough time. You can keep on this section. Yeah.
Okay. Yeah. So I just want to maybe just show you two slides about other research direction that my group is very interested. So, like in my first part or in my major part, I show you how we want to use nonlinear optical probe to measure topology, but we'll also use it to measure like other like order parameter. Okay, so one thing that we're particularly interested in is that whether we can measure the long range order in antiferromagnet directly. So what we measure, what we study is a magnet called manganese phosphor selenium 3. So it has neo antiferromagnetic order. So this is the one of the layer. Then it has like ABC stacking. So then actually in the monolayer it has mirror symmetry. But if you consider the rhombohedral ABC stacking, it break all of the mirrors. But key thing here is that actually the lattice, even though it break all of the mirrors, but the lattice is central symmetric. But you can see the spin order break inversion. So when the spin order break inversion, it also allows second order generation, and we can use second order generation to detect the long range order in the monolayer antiferromagnet. So another thing is that actually this magnet is XY model. So originally we thought we won't see the transition in the monolayer, because in the XY model, what happened is a causeless solid transition. So it won't have a long range order parameter. So then what's interesting is that what we found in the active strain, so because we do exfoliation, the strain is inevitable. So what happened is that active strain make the system kind of develop a XY order instead of develop the icing order due to the strain, because the threefold rotating symmetry reduced to like twofold by the strain. So actually what we see here is the icing order. And also we can, another nice thing about the second generation is that so we can use polar patterns and we can figure out the neo vector direction. So here we can see that we can really image the domains, and we do really thermal cycle. We heat a sample about the neo temperature and cool down. You can see we can really see different domains. So these arrows are different neo vectors. We can image neo vector switching. And that's it. So strain plays a very important role here. And what we did is that we really extreme. So we really use the strain to stretch the sample. For example, you can see that so this is the strain direction, and maybe I didn't say here. So this is actually the neo vector direction on the node direction. So you can see that the neo vector direction is follow the strain direction, and this can also be explained by the XY model with strain. Okay, and this is what developed by my colleague Charlie Kim and Jim Lee. So basically here we just show that strain can stabilize the long range order in XY magnet in the 2D, which is icing order, and we can switch the domains by strain and also by heat and image them by second generation. Okay, so maybe let me summarize my talk. My talk is mainly about cobalt silicon, and it's about the CPGE. So the key message is that we figure out that the role of the chemical potential is very important. So when it's cut the flat band, it's not quantized. I mean, even though it's large, it's not quantized. And in order to see the quantization, we need to dope the chemical potential above the flat bands, and we also actually need to we also need to have very long hot carrier lifetime that we hope we can achieve in cobalt silicon. Okay, yeah, thanks for your attention.
Okay, thank you. So I think if any of the audience have any question, you can unmute yourself and direct ask Professor Liang. So
yeah, so I had a quick question. I think I missed it. Would you maybe go over again why you need a very long hot carrier lifetime?
Yes. So because what quantized? Yeah. So what's quantized is the DJ over DT. Yeah. So what's quantized is what people call injection current. So basically, you want to kind of excite from the kind of field band to the empty bands. And okay, so what's quantized is this process. You excite from field band to empty bands. Then before it relaxed. So if you plot J versus T, before reach tau, the J is a linear function of T. And what quantized is that slope.
Yeah, sure, of course, yes, yeah.
So then we hope
so
that
why do you need a long hot carrier lifetime then?
So then basically it will stay there for longer before we can measure it by time resolved Terahertz emission. Maybe
okay, so I see. So you are sensitive to J and not DJDT, even though you have, because I would have thought that you'd also be sensitive to DJDT in your terahertz emission, but you're mainly sensitive to J, I guess, because that's the thing that is causing your terahertz emission. Is that what you're saying?
Right. So even though in the far field we are measuring DJ over DT. Okay, so maybe let me give you another reason which might be better. So even though terahertz emission is proportional to DJ over DT. So then I mean, so basically the relation is really like this here. So we have both quantity. We have beta XX and a tau.
Correct.
Okay. What we want to extract is beta XX. And if this tau is very short, it's basically featureless. We cannot extract beta XX. We need to either we need other measurement, like a time without measurement to measure tau. So then we don't need a long hot carrier lifetime.
I see.
But if we only do this, it's better for this to be long and have a frequency dependence here. So then we can fit the data and figure out tau and beta XX.
I see. And maybe just to kind of clarify a bit more, this tau, what exactly is this tau? And I know you use the word hot carrier lifetime, but if you're exciting very far above the Fermi energy, and these are very, primary photoexcited carriers are very high in energy, then there are many processes that allow for their relaxation. For example, the initial photoexcited cascade, including, for example, electron-electron interactions as well. So maybe you could say something about what this tau exactly is.
Right. So I think a tau. Right. Okay. So I think this is a very good question actually, and I would say this tau is mainly is not really the initial like a fast relaxation. I think I would say it's the latter. It's really the slow relaxation. I would say maybe. Sorry. First, I want to emphasize I'm not particular kind of clear on this part, but I would guess is really if you excite on the top, sorry, to the top band, it really relax down. So I think it's that tau. That's my guess. But
so it's the final slow relaxation rate that you think?
Right. Yeah, I mean initially, as you said, it's very fast. It's not that.
Yeah. So why do you say that? The reason why I'm a bit skeptical about that, it could be that you're right, but I mean, in the interest of maybe having an open discussion about it, is that whenever you think of injection current, which I think is what you're looking at right now, it comes from I believe it comes from the difference in velocities between valence and conduction bands, or whichever bands that you're exciting out from, right? And
right.
So once you get in, so that comes from the difference in velocities of that particular, momentum surface that you're exciting, maybe at 1 eV or something. The question is, once it relaxes away from that momentum surface, would you expect that difference in velocities to be maintained, or is that destroyed by the relaxation process? Just a question. I actually honestly don't know the answer.
So sorry, you're saying that after you relax?
Yeah. So the question is, does that change in velocities? Is that maintained after you relax, or?
I mean, my guess is it won't. I mean, you have many kinds of like scattering. My guess is that it won't maintain the velocity because you have many kinds of scattering.
Yeah, that's right. So that's why I'm asking a question about what the one over tau is.
Yeah. So I think here we are talking about the slow. So if you did pump probe, it's really the slow decay, not the initial fast degree.
I see. So you're saying the initial photoexcitation cascade, the relaxation from the high energies, will not relax the current?
No, I'm not sure, but.
I see. No, I frankly have no idea as well. So.
Yeah. So actually, So I mean, I also have to be honest. I mean, since we're not in that regime yet, so I have not really thought about that.
I see. Okay.
Yeah.
Thanks.
Because I mean, the next step is really. I mean, we really try to figure out. We really hoped to measure the tau here, but we didn't, and we also haven't done pump probe yet. But okay, maybe I want to put another note. So here, the quantized CPGE is less robust compare with the quantum Hall effect. So you talk about like electron, maybe scattering or electron interaction. Actually, the interaction will also destroy the quantization here. Actually, it's not like a quantum Hall.
Yeah.
So actually, and not. I mean, we're still trying to dope them and measure low temperature, but I don't know what we will see in the end. Actually.
I see. Okay. Thanks a lot.
Okay, thank you. Any other question from the audience?
So I have a quick question. So for your so you use this frequency transformation to get the energy, right? So before you measure the time domain.
Yes.
Yeah. So you think this is emitted frequency, the emission frequency, right?
Right.
So the excitation frequency is fixed.
Yeah, sure. So for example, this purple curve, the excitation frequency is 0.25 eV. You have a pulse.
So is there any way to really measure this in the spectrometer or something?
Measure what?
Measure the spectrum, or the emission spectrum.
You mean?
In the frequency domain, because this one you get it from the time domain, right? You use a Fourier transformation to get.
I don't think there's a. No, I don't think there's wait, let me think. No, I don't think there's a spectrometer that you can measure. Like in the. So I mean, you have to use some.
This is 0.8 eV should be okay, right? This is like infrared regime.
Yeah, but how can you measure at different frequency at like across range? I mean, you need to have some interferometer in the like so actually 2 terahertz is 8 millieV. It's very hard for like FTL already actually. Maybe there is a method, but then I'm not very clear actually. But in this regime, like the usually. Like when people use like for FTIR, they use like global, like a mercury lamp. So the intensity is like 1,000 times lower than the terahertz pulse, terahertz source. So
because
maybe those spectrometer will work, but I'm not sure.
Yeah, I'm wondering whether because you try to feed the tau and try to feed the beta XX, like in Justin's question, right? So whether this tau really changes with omega. If it really changes with omega, you cannot feed a tau, right? Because yeah.
You mean sorry? When you say this tau change with the little omega or big omega?
With this both omega, I think, right? So because you fix your excitation, then your emission place is different, then this relaxation time will be different.
Yes. So what I can tell you that definitely this tau will depend on this excitation frequency. So this actually I'm very confident that. So, but here, I mean, in this regime, I don't know. Yeah.
Okay.
Okay. So I have a question. So actually, here you are measuring the radiated terahertz pulse instead of directly measuring the DC current. But actually, I think most people working on nonlinear optics, they don't have this technique. So what is a suggestion for them if they want to measure this effect by directly measuring the DC current?
Yeah, so there are a few. Yeah, so I think if you want to measure in a DC current, so what they really measure is this actually. It's J is equal to like intensity, then you get this eta. But there are a few kind of a complicated thing. Is that so here? Okay, so here is the longitudinal photocurrent. So then actually you need to put contact like on top and in the bottom. So yeah, so I don't. I mean, and as I said in my talk, we are not really expert for the DC current. So I think if you put contact on the top and bottom, and it's so basically you need to know the accurate photocurrent. If you do DC current, so you're measuring beta x and tau, and you need to make sure that you really measure the kind of the local response, because as I said here, so. No. Where's the wrong place? Yeah. So if even for the transfer CPGE, if the laser spot is smaller than the sample, you're going to deal with like the non-local response. And in other words, we want to measure J is equal to sigma EE, but in this kind of measurement, the J. So you have intensity, right? You have E squared and you have J, but if you use J divided by the intensity, is not really the response function, but but some other non-local response. So I think it's just complicated. I mean, if I don't know whether people can measure like longitudinal CPGE in DC transport like very well. So that's first thing. Second thing is that of course, I mean in transport you're still measuring the beta XX times tau. So one still need to figure out tau by like time resolved measurement. And another issue another difficult thing in the DC photocurrent, I mean even in this transverse photocurrent, that when you change wavelength, actually the laser spot will move, and then it will kind of change the heat kind of distribution. So that's also a complicated issue actually, because for us we don't have that problem. We really measure the local response. So I think in order to measure spectrum, I think the Terahertz emission is a much better way than the DC photocurrent. I mean, I'm confident that if one is expert in DC photocurrent, they can deal with this issue. But yeah, one has to be really careful actually. But yeah, and I mean, Terahertz emission is yeah, as I said, it's not a new technique. I mean, we just push in the middle infrared, but many people can. I wasn't, but not many, but I think a handful of group can do that. Yeah.
Okay. Any other question from the audience? Okay, if no questions, then let's call it a day. Thank you. Thank you for the nice presentation.
Yeah. So just
you know, if you want to know, if you want, if you have like 10-20 minutes, I